Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 4 called the Elimination Method. So all throughout this unit we've been working on systems of equations and eventually we'll segue to systems of inequalities soon. But today we're going to look at a new technique that we talked about the basis of in the last lesson, known as the elimination method. And this is a particularly nice method of solving a system of two equations with two unknowns. So let's jump into it and learn how to use the system of elimination. Now, the method of elimination, we can solve systems by eliminating one of the two variables. And we can do this often by remembering a couple things about the solutions to systems of equations. So let's take a look at that. Right, solutions to systems remain solutions if, one, properties of equality are used to rewrite either of the equations, and two, the equations are added or subtracted, or any rewrite is added or subtracted. All right, so let's kind of get into that. The method of elimination works if you add the two equations together and one of the two variables cancels out. You sort of have the opposite of it in the two equations. Now, most of the time that's not the case. So very often you have to take one or perhaps both of the two equations and most of the time multiply both sides of that equation by some constant in order to get those opposites. It sounds kind of complicated, but it's actually quite easy and oftentimes is even easier than the method of substitution to solve a system of equations. So without further ado, let's get right into it. Now, you may want to have a calculator handy today just to do sort of routine calculations. I'm going to actually just use a scientific calculator today and throughout most of this course to do routine calculations. When we need our graphing calculator to do graphing and other things like that, we'll bring that out, but we won't need that today. So let's take a look at exercise number 1. Consider the system shown below. Solve the system two ways, by eliminating x in A and by eliminating y in B. All right, so let's talk about this, right? When we look at this system, it's 4x plus 5y equals 12 and negative 2x plus y is equal to 8. Now, let's just say I added these two equations right from the beginning, all right? That's not going to get me very far, but let me show you what happens when we do that, if I can actually get my board to behave. All right, so if I added these two equations, I'd have 4x plus negative 2x, and that would be positive 2x. And then I'd have positive 5y plus positive 1y, and that would be positive 6y, and positive 12 plus positive 8 would be positive 20. Now, there's nothing wrong with that, and absolutely anything that solves this system of equations would also be a solution to the equation I just wrote down. But the problem is none of the variables got eliminated, so it really doesn't do me any good. So I'm going to erase all of this. I hope you didn't write that down. I'm going to erase all of this, and I'm going to be thinking about this system, and I'd like to eliminate the x variable. Now, the reason, of course, that x wasn't eliminated when I added these two things together was that I had a positive 4x in the first equation and a negative 2x in the second equation, and those aren't additive opposites. But if I take my second equation and I multiply both sides by 2, I will end up having a negative 4x in the second equation, a positive 4x in the first equation, and when I add them together, they will eliminate the x. So let's take a look at how that's done. All right, so I take this first equation, or that second equation, and I'm going to multiply both sides by 2. That's just a property of equality. Now I have to make sure I multiply the entire left side, negative 4x plus 2y, and I really need to remember to multiply the right side. I want to be very clear about something. Since I used a property of equality to manipulate that second equation, this equation has exactly the same solutions as that one does. So I can now use it to help me solve this system. What I'm going to now do is I'm going to take the first equation and I'm going to write it right underneath this. It doesn't really matter which one goes first and which one goes second. I'm going to take that first equation now and write it down as 4x plus 5y is equal to 12. I now can add these two equations, and when I do, the negative 4x and the positive 4x cancel, right? They're equal to 0. On the other hand, 2y plus 5y is 7y, 16 plus 12 is 28, and notice the beautiful thing that's happened now. The x's are gone. All I have now is an equation that involves y and a very simple equation that involves y. All I have to do to solve this now for y at least is divide both sides by 7, and 28 divided by 7 is 4. Now whenever we solve a system, we don't want to find just the value of one variable, we want to find the value of both variables. So at this point what I'm going to do is I'm going to take y equals 4 and I'm going to either substitute it into the first equation or the second equation. Doesn't matter which, take your pick. If one of them seems like it's going to be easier to work with, go with that one, but it should not matter. So I'm just going to take y equals 4 and I'm going to throw it back into the first equation, which is going to allow me to solve for x. Now that first equation, 4x plus 5y equals 12. All right, let me get a little bit more room here. I can now take my y equals 7, put it into this equation, and once I do, all I have are x's left. So I get 4x plus 35 is equal to 12. I'll subtract a 35 from both sides. Be a little careful there if you're not using your calculator, right? 12 minus 35 is going to be negative 23. Something seems wrong here. What am I doing wrong?
Y is 4.
Y is equal to 4. Y is not equal to 7. I don't know where 7 came from there. That was a little bit weird. Oh, the 7 came from right up there. All right, so here we go. Y is equal to 7. Y is still equal to 4. Still not equal to 7. Apparently it's a very early day for me. Here we go. 20, 20, and 20. Thanks to my producer, Joey. Here we go. 12 minus 20 is negative 8. That works out a little bit better. Divide both sides by 4, and x is equal to negative 2. All right. So the solution to my system is y equals 4, x equals negative 2. Woo! Too early. I need more coffee. All right. So, the bigger point, besides my inability to substitute the correct value into this equation, is that the idea is if we've got opposites in the two equations and we can add them together, those opposites will eliminate each other and we'll be left with only one variable. Once we have one variable in theory, and its value, it's easy enough to substitute that into one of the two equations and solve for the other one. Now, what I wanted to illustrate also in this problem is it doesn't particularly matter which variable you eliminate first, all right? So we're going to go through the same problem. Hopefully this time I won't make a mistake. We're going to go through the same problem, but this time we're going to try to eliminate y. Now, when we look at the system, we've got 4x plus 5y equals 12, and negative 2x plus y is equal to 8, right? So before, I multiplied the second equation by 2. But let's say I take this second equation and I multiply it by negative 5. Now if I did that if I multiplied this entire equation by negative 5, then this y would have a coefficient of negative 5 on it, and I'd have negative 5y and positive 5y, which would cancel each other out. So let me move this out and let me do that. Let's take this equation now, this second one, and instead of multiplying it by 2, let's multiply it by negative 5. All right, when we do that and we distribute, negative 5 times negative 2x, I need to be careful with, that's positive 10x. Then I've got plus negative 5y, and 8 times negative 5 is negative 40. Again, I'm going to take my first equation and just write it right underneath it. 4x plus 5y is equal to 12. When I add those together, I'll get 14x. Again, the negative 5y and the positive 5y, when added together, would cancel. And I'm going to end up getting negative 28. Negative 40 plus 12 is negative 28. Divide both sides by 14. Negative 28 divided by 14 is negative 2. Now, I knew already that x was negative 2. I had already solved for that in the previous problem. But here we see that we can eliminate the y and solve for the x. We can then take that x and we can plug it into either of the two equations, which is where it went terribly wrong for me last time, and then solve for y. So let me do that really quickly, and I'm going to do it again. I'm going to take my x equals negative 2 and I'm going to substitute it into this equation. That's the first equation, right? So if I do 4 times negative 2 plus 5 times y is equal to 12, I'll get negative 8 plus 5y is equal to 12. Add 8 to both sides to get rid of that negative 8. I'll get 5y is equal to 20, divide both sides by 5, and y is equal to 4. All right? So it really doesn't matter. You can always manipulate either equation to eliminate one of the two variables. Now, sometimes it's easier than others to eliminate one or the other variable, and we're going to be playing around with that some today. So sometimes it's clear that one of the variables will be easier to eliminate than the other, although again, 100% of the time, we could eliminate either. It just can get very messy if we choose the wrong one. So we're going to practice on understanding which one is better to eliminate. So let's take a look at exercise number 2. Consider the system shown below, 3x plus y equals 18, and negative 2x minus 2y is equal to negative 8. Letter A, which variable can be eliminated by altering only one of the equations? Only one of the equations. So pause the video now and think about how you could just modify one of the two equations to eliminate one of the two variables. Pause the video now and consider that. All right, well, the answer is I really could eliminate either variable. I could. But what would be very, very easy is to multiply the first equation by 2. Now, if I multiplied both sides of the first equation by 2, I'd have 6x plus 2y equals 36. And I'd have a positive 2y here and a negative 2y there. It would be a lot harder to make this negative 2x into a negative 3x or make this 3x into a positive 2x. That would be harder. You could do it with fractions, but it would be more difficult. So, which variable can be eliminated by altering only one of the two equations? We could eliminate y by multiplying the first equation by 2. All right? So, letter B, solve the system of equations. All right, let's do this one again together, all right, so that you can get a little bit more practice. So I'm going to take that first equation, and I'm going to multiply both sides by 2. All right? Again, be very careful to distribute the 2, so I get 6x plus 2y is equal to 36. And now I'm going to take that second equation, not alter it at all. Negative 2x minus 2y is equal to negative 8. When I now add them together, all right, 6x plus negative 2x is positive 4x. 2y plus negative 2y is 0. And 36 plus negative 8 is 28. Again, look at how that y cancels, right? It's eliminated. I divide both sides by 4, and I find x is 7. All right, that is a very, very common thing. In other words, once you've got those additive opposites, 2y and negative 2y, when you add those two together, you always get an equation that kind of looks like a number times a variable equals a number. And all you have to then do to solve the problem, or at least solve for the value of that variable, is divide both sides by whatever coefficient is multiplying the x or the y. I mean, it's super duper easy. Then, of course, maybe even the harder part, apparently for me, is taking the value of that variable, substituting it back into one of the two equations to find the other one. So let's do that now. Let's take x equals 7, and wouldn't make a difference, but that second equation's got negatives all over the place. I'm bad with negatives. So I'm going to take that x equals 7, I'm going to substitute it back into the first equation. So I'll take this thing and throw it into here, which then I'll put down here. Aren't my arrows helpful? So I'll do 3 times 7 plus y is equal to 18. 3 times 7 is 21. 21 plus y is equal to 18. Subtract 21 from both sides, and y is equal to negative 3. All right. Now, by the way, this system of equations could certainly be solved both graphically and by substitution, right? So I could solve them graphically, but I'd have to rearrange both of these equations into y equals mx plus b form. That'd be a little bit annoying. And I could solve it by substitution, but by substitution I'd have to take one of the two equations, solve for y or x, and then substitute it into the other equation. Again, it can certainly be done, But when both variables are on the left side of the equation, right, as they are in this situation, in both equations, then it makes a lot of sense to try to use elimination. Okay. Now, we've really got one more thing to consider. Sometimes it will make sense to alter both equations before adding them to eliminate the variable, okay? Many times that will make sense, and that's easy enough. Let's take a look at exercise number 3. Solve the following system of equations by elimination and check that your answer is a solution to the system. All right, so we've got a couple things to do here. We want to solve the system and we want to check to see if our answer is in fact correct. So I've got 5x minus 2y equals 10 and 2x plus 7y equals 43. Now, I could eliminate either the x's or the y's, all right? Now, if I want to eliminate the x's, maybe I could make the x coefficient in the first equation equal to 10, right? I could do that by multiplying both sides of the equation by 2. I could make the x coefficient in the second equation equal to negative 10 by multiplying both sides of that equation by negative 5. Now, don't get me wrong. You could also get a negative 14y in the first equation by multiplying both sides by 7, and a positive 14y in the second equation by multiplying both sides by 2. Maybe that makes sense to you. That would be completely okay as well. I'm going to eliminate the x's in this case, but if it feels more comfortable for you to eliminate the y's, you go for it. So here we go. This first equation, I'm going to multiply both sides by 2. And this second equation, I'm going to multiply both sides by negative 5. All right, so what does my first equation become in this case? It becomes 10x minus 4y is equal to 20. All right, that's simple enough. My second equation becomes negative 10x minus 35y. And let's see, that would be negative 215. Don't hesitate to use your calculators on this. It may save you from making mistakes. All right, so what happens? Well, when we add these two equations together, the 10x and the negative 10x are going to cancel. Negative 4y plus negative 35y is negative 39y. And positive 20 plus negative 215 is negative 195. All right, now I will divide both sides by negative 39. This might be where we want to pull out the calculator. Here I've just got a simple scientific calculator so that you can see the digits a little better. Negative 195 divided by negative 39, not surprisingly, gives me a y value of 5. Okay, let me just move my TI Smart View out of the way. Right, now that we've got our y equals 5, we can substitute it into the first equation, the second equation, or even into either of these two equations. It doesn't really matter. Whichever one strikes you as being easier to solve for x gets the job done. So I think I'm going to take that y equals 5 and just substitute it into the first equation. All right, that's going to give me 5x minus 2 times 5 is equal to 10. 5x minus 10 is equal to 10. Add 10 to both sides. 5x is equal to 20. Divide both sides by 5. And x is equal to 4. All right, let me move that out of the way. All right, simple enough. By the way, in theory, you could even solve for the second variable by going back and doing elimination a second time. So you could be like, well, I'm gonna eliminate. I mean, I think that's more work than it's worth, but you could like eliminate to get y, and then you could go back and eliminate to get x. I think it's simpler to just take the value of y, substitute it into one of the two equations and solve for x, but it doesn't really matter. Now, one of the other things that the problem told us to do was to check to make sure that this is in fact a solution. And I think that that makes a lot of sense simply because we're doing a lot of manipulation here, right? We're doing a lot. So let's go back and check to make sure this is in fact a solution. Now, we've been doing this throughout the entire unit, right? So in order to check, I want to take my first equation, 5x minus 2y is equal to 10. And I just want to make sure that x equals 4, y equals 5 is a solution to this particular equation. So I'll just substitute them in. I'll get 20 minus 10 is equal to 10, and 10 is equal to 10. So that one checks, that's good. But I've got to make sure it also solves the second equation, so that's 2x plus 7y is equal to 43. That's going to be 2 times 4 plus 7 times 5 is equal to 43. That's 8 plus 35 is equal to 43. And that is, in fact, 43 equals 43. All right. So it works. Excellent. It's all good. All right. So very often, not always, but very often in a system of equations like this, we have to modify both equations in order to get those additive opposites. And again, there's oftentimes many different ways to do it. Excuse me there. All right, so let's take a look at a very, very similar problem, except one that involves A's and B's. Let's take a look at exercise number 4. Solve the following system of equations by elimination and check that your answer is a solution to the system. Awesome. Great. So what I'd like you to do now is pause the video, take a look at the equation, decide which variable you want to try to eliminate. You will have to modify both equations in all likelihood, unless you really love your fractions. All right, you'll have to modify both of these equations. Do the elimination, and then I would pause before you do the check, because we'll go through it and then we'll do the check. Pause the video now and take up to 5 minutes to try to solve this system. All right, let's do it. So, do I want to get rid of the A's? Do I want to get rid of the B's? I think last time I got rid of the X's and solved for Y. I think this time I'll get rid of the B's and solve for A. In this particular one, I've got a 5B, and this one I have a negative 4B. I can make those both into a 20 and a negative 20, right? I can make this one into a 20 by multiplying both sides of the equation by 4. I can make this into a 20 by multiplying both equations by 5, or both sides of the equation by 5. So, let's do it. I'm going to do 4 here, 4 here, 5 here, 5 here. My first equation then becomes 8a plus 20b is equal to 4. My second equation becomes negative 15a minus 20b is equal to negative 60. Okay, when I add these now together, 8a plus negative 15a will be negative 7a. 20b plus negative 20b will cancel, and 4 plus negative 60 will be negative 56. Divide both sides by negative 7. Keep in mind, right, a negative divided by a negative is a positive. Negative 56 divided by negative 7 gives me A is positive 8. All right. Now, side note, because I let you just go ahead and work on this on your own, some of you very well may have said, well, I'm going to multiply the first equation by 3 on both sides, and the second equation by 2 on both sides, giving me a positive 6a and a negative 6a and eliminating the a. Awesome. If you did that, cool, right? I decided I wanted to get rid of the b's. Now, I still have to go on and solve for b, so I'm going to take a equals 8 and I'm going to throw it back into my first equation. Again, doesn't really matter. So I'll have 2 times 8 plus 5b is equal to 1. 16 plus 5b is equal to 1. Subtract 16 from both sides. 1 minus 16 is negative 15. Divide both sides by 5. And negative 15 divided by 5 is negative 3. All right. And that's what you would have gotten, of course, directly if you had eliminated the a's to begin with. Now, of course, to do the check, we would do exactly what we did before. We'd take a equals 8 and b equals negative 3. We'd substitute it into both equations, make sure that they're both true, which I guarantee they would be. So I think we'll skip that step right now for time's sake. Now, that being said, obviously, if the problem says that you should check that your answer is a solution to the system, please do check that your answer is a solution to the system. All right, let's do one more problem. Now, we're going to get a lot of work in the next lesson with problems, word problems that involve systems of equations, some of which you'll solve using elimination, others you may solve using substitution, all right? But here, we're going to take a look at a word problem that you can solve by elimination. Let's take a look at exercise number 5. Two numbers have the following properties. The sum of the larger and twice the smaller is equal to 13. When 3 times the larger is decreased by the smaller, the result is 18. Letter A, model the information given in this problem with a system of equations. Carefully define your two variables using let statements. All right, Well, what I'd like you to do is, choose a variable for the smaller number, choose a variable for the larger number, throw down let statements for those, and then just try to model what they've given you in the problem with a system of equations. Don't worry about solving it. We'll do that in letter B. Pause the video now and go ahead and do that. All right, well, choose XY, choose AB, choose whatever. I'm going to go a little more descriptive. I'm going to let L be equal to my larger number, and I'm going to let S be equal to my smaller number. All right, so what do I know? The sum of the larger plus twice the smaller is equal to 13. All right. When 3 times the larger is decreased by the smaller, the result is 18. All right? There it is, right? I mean, we just literally just translate exactly what they've told me. The sum of the larger plus twice the smaller is equal to 13. When 3 times the larger is decreased by the smaller, i.e. we subtract it away, we get 18. And look at how natural it will now be to solve this by elimination. And that's exactly what I'd like you to try to do in letter B. Pause the video now and try to solve this system, including your variables, for letter B. All right, well, this is kind of a nice one because we only have to actually modify one of the 2 equations, and it's easy to do that to eliminate either one of the variables. For instance, I could multiply the first equation by -3 to get a -3L here that would then eliminate the positive 3L there, or I could multiply the second equation by +2, giving me a -2s here, which would eliminate the positive 2s there. And I think that's actually what I'm going to do. So I'm going to take that second equation, 3L minus S is equal to 18, and I'm going to multiply both sides by 2. That's going to give me 6L minus 2S is equal to 36. Now I'll take that 3L, that's actually the same equation. Then I'll take my L plus 2S is equal to 13, and I will move all of this stuff out of the way. And now I can add them together. 6L plus 1L is 7L. 36 plus 13 is 49. Divide both sides by 7. And L, the larger number, is equal to 7. Excellent, right? How easy is that? Now what I'd like to do is I'd like to take my larger number equal to 7 and I'd like to figure out what my smaller number is. I think this time I will plug it into this first equation. Remember, L is equal to 7. So I'll have 7 plus 2s is equal to 13. I'm going to subtract a 7 from both sides. That's going to be 2s is equal to 6. Divide both sides by 2. And s is equal to 3. So I find my larger number is equal to 7, and my smaller number is equal to 3. Awesome, right? And again, very easy in this case because we only had to modify one of the 2 equations in order to get those additive opposites that when we add, they just go away. They end up equaling 0. Okay, so let's summarize, right? The method of elimination. This is going to be the last method that we have for solving systems of equations, right? We have the graphical method by finding intersection points. We have the substitution method by substituting one equation into the other equation. Interestingly enough, substitution also eliminates one of the variables. And then we have the elimination method, which we do by adding 2 equations and hoping that we have additive opposites that will cancel each other out and leave us with just one variable. Now, if we don't have additive opposites right away, and most of the time you don't, most of the time, not all of the time, most of the time you don't have additive opposites, right? Then you have to modify one or both of the equations by just using the multiplicative property of equality, right? We just multiply both sides of the equation by some number to produce those opposites. Once we've got the opposites, we add the equations together, eliminate one of the variables, solve for the other, take that value, plug it back into one of the original equations, and solve for the second variable. We'll get a lot more practice on this in the next lesson when we do word problems involving systems of equations. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.